Alright, Assalamualaikum and a very good evening or maybe good morning to my students at Saudi Arabia. Okay, so I will do a unsynchronized class because my health is not so good yesterday. So I have to record this chapter for you guys to listen to my lecture first, and then we will have a Q&A session after this. All right, maybe in our WhatsApp group, okay, or in our next synchronized group. All right, so the next chapter is about the analysis of the organic and inorganic analytes using the spectroscopy based methods. All right, so this topic will introduce the spectroscopy method, the principles, and a little bit about the UV visible instruments. All right. So previously in the first chapter we have learned about the basic analytical introduction to the sampling and sample preparations, and then we have learned about these basic calculations in the analytical chemistry. All right, and then now we will introduce about the first concept in the analytical technique, which is the spectroscopy method. All right, spectroscopy based methods. All right, and we will learn about the principle of the spectroscopy. Okay, we have different types of analysis. Okay, as I told you in the Kahoot quiz or in our first quiz. All right, the classical methods is gravimetric analysis and volumetric analysis, and we have the instrumental methods, which is the spectroscopy, chromatography, and electroanalysis technique, right? Okay, the instrumental methods, right? The methods that exploit physical properties of an analyte to obtain a qualitative. Qualitative is what is the analyte, and quantitative, how much is the analyte. Information by using modern instruments. What are the modern instruments? The modern instruments are based on the spectrometric methods. Okay, a group of instruments that based on the atomic and molecular spectroscopy, and we will learn about spectroscopy as well, the study, okay, or the science that deals with the interaction of various types of radiation with matter. So basically the spectroscopy is about the science, the study, or the knowledge about the interaction between the various type of radiation with the matter. Okay, the matter is what in this course? Of course, the analyte is the matter. All right, so spectroscopy and spectrometry methods. All right, the spectroscopy also the study of the properties of matter through its interaction with different frequency components of the electromagnetic radiation. So in spectroscopy technique, okay, most of the topic will discuss about the interaction between the different frequency of the components in the electromagnetic radiation. So we apply electromagnetic radiation in order to analyze qualitative and quantitatively our analyte. All right. Okay, so type of electromagnetic radiation. Okay, we have from low to high frequency. Okay, we have the extremely low frequency LF, we have very low frequency VLF, radio wave, microwave, infrared radiation, visible light, ultraviolet radiation, X-ray, and also the gamma rays. That is the electromagnetic radiation type. All right, and each type of spectroscopy use different light frequency and give a different picture. Okay, the spectrum itself we call as a picture. All right, so different type of light frequency will give the different picture. All right, so the spectroscopy is the study of the properties of matter through its interaction with the different frequency components of the electromagnetic radiation, includes the interaction with other forms of energy. So the general methodologies are adapted in various ways to extract information, including energies. Okay, the energies in the form of electronic, vibrational, or rotational, the structure and conformation of molecules. Okay, and then the dynamic properties of atoms and molecules. Okay, this is the general methodologies adapted Okay, various way to extract information, right? And then the spectrometry is the measurement of intensity, okay, in terms of absorption, emission, and also a scattering of light, okay, radiation by matter using electromagnetic or photometric device as in this spectrophotometry. All right, so we flash back to the our previous knowledge about the wave properties of electromagnetic radiation. So the electromagnetic radiation is a form of energy whose behavior is described by the properties of both wave and particles. So the basic thing we have to know is the wavelength, okay, the vibration that contribute to the wave, right, and then the direction of the propagation, the wave motion of electromagnetic radiation. So the optical properties are explained by describing light as a wave. Okay, so interaction between radiation and matter, for example absorption and emission, are described by treating light as a particle. Okay, so in the spectroscopy methods, we just imagine, all right, we have to describe, or we have to bear in mind that in this topic we treat the light as a particle. Okay, so it can be absorbed or emitted. All right, then we will learn how the light, okay, in the specific energy, with a specific energy, will absorb and emit. All right, and then it can be translated into response of the qualitative and quantitative of our energy. Okay, so light is characterized by a different frequency and wavelength. Okay, remember wavelength is lambda, the distance of one cycle, and then we have frequency v, okay, is the number of cycles passing a fixed point per unit of time. So the equation is lambda is equal to c, where the c is the velocity of light, okay, and divide by v, okay, the frequency. The electromagnetic radiation consists of quantum of energy, okay, a packet of energy, okay, discrete packet of energy, or photons. Okay, remember this a packet of energy or quantum of energy is absorbed or emit differently, okay, with one another among the analytes. So that's why we could differentiate between analyte A and analyte B or C with the amount of the energy, quantum packet of the energy, right, the discrete packet of energy, or also known as photons. All right, during interaction with atoms or molecules, the energy wave behave like a particle. Remember, we have to bear in mind, okay, we assume that the energy wave behaves like a particle in this kind of spectroscopy knowledge to understand the process of absorption and emission of the energy, right? So E equal to hv, where h is a Planck constant, all right, and E, so that E is equal to hc divided by lambda, okay, because wave number, okay, v is equal to 1 per lambda. So the shorter the wavelength, the higher the energy. This is basic knowledge of the wavelength. The shorter the wavelength, the higher the energy. This is why UV radiation from the sun can burn. All right. Okay. So the wavelength and frequencies of the electromagnetic radiations, we can see there. Okay. Where is the visible region? Okay. So why is spectroscopy useful in analytical chemistry? Okay. Why? Because a technique used for detection. Spectrometry, okay, the spectro meaning of the light, okay, spectrum, metry is measurement, okay, so we measure the measurement of the energy in terms of light. Okay, a group of instrumental methods using spectroscopy. We have a UV visible instrument, okay, we can detect we can describe our sample in terms of the absorption of the UV light. Okay, we also have infrared instrument that can absorb our sample absorb the energy from the infrared wavelength and can we can see the absorption in the infrared spectrum. Okay, so interaction of matter with electromagnetic radiation, we have several types. Okay, the first type is to take up our analyte or our matter, okay, absorb the energy, a transition or excitation from a lower energy state level to a higher state with a transfer of energy from radiation field, example flame, to an absorber, example atoms of a metal. So in the absorption concept, our matter, okay, our analyte absorb the energy, all right, and then absorb the energy from meaning that the matter is from the lower energy state level become higher state level, okay, with transfer of energy from radiation field. Okay, for example flame. Okay, for example, we burnt our analyte in a flame, so the matter will be excited from the lower and energy state to a higher state, okay, and then our absorber, okay, the atoms of metal, we absorb the light, okay, the light in the form of wavelength, so that the detector can detect that the light from the light source, okay, the light source emits a light and then absorbed by our analyte. The detector will detect some of the energy have been absorbed. So how much is the energy is represent what is the analyte. How much of the energy represent how much is the analyte. Okay, and then what is the specific wavelength of the energy, describe type of the analyte. So the second one, we have emission, to give off. It is a transition state, that relaxation from higher state. Okay, the emission concept, we have our matter, our analyte. It will be excite using flame and so on. Okay, and then after the matter being excited, okay, it will come back to the lower state. Okay, and from excited state to the lower state, it will release a packet of energy. Okay, and this packet of energy will be detected by the detector, and then the detector will translate into the for example, the first one is the wavelength of the energy will describe type of the analyte, and what do you call that, how much is of the wavelength being absorbed, okay, being detected at the detector will represent how much of the analyte. Okay, and the third one, we have a scattering, a redirection of light due to its interaction with matter. Okay, it is might or might not occur with transfer of energy, and might not have different wavelength from incident light. Okay, this is the illustration of energy change associated with the absorption of electromagnetic radiation. Okay, E0 is ground state and E1 is the first excited state. Okay, all right. We have A is a pure rotational change, okay, far infrared. We have B, rotational vibration change, okay, near infrared, and C, rotational vibration electronic change, which is a visible or UV. Okay, this is a type of wavelength. Okay, we can see, okay, all right, from we have an example of the ground state and excited state. Okay, what is the difference between absorption and emission? Okay, absorption is we measure the energy that been absorbed by the matter after it's being excited. Okay, and then what about emission? We measure the energy that released by the matter after it being excited, and after it excited and come back to the ground state. Okay, possible type of transition. Okay, ultraviolet UV, electronic transition, near infrared, near IR is vibrational transition, Okay, a visible spectrum is for outer electron, far infrared is for rotational or vibrational, and microwave is for rotational transition. Okay, this we have a type of spectroscopy: gamma, X-ray, vacuum, ultraviolet, and so on. And we have example of spectrometry methods. Okay, if the properties is emission of radiation, the method is emission spectroscopy. Okay, like X-ray, UV visible, fluorescence, and also phosphorescent and also luminescent. And if we have if the properties are absorption or radiation of radiation, we have spectrophotometry and photometry method using X-ray, UV visible, and also IR. We have nuclear magnetic resonance (NMR), and we have electron spin resonance (ESR). If a scattering of radiation, we have turbidimetry and Raman spectroscopy. If refraction of radiation, we have refractometry, interferometry, and we have, if the diffraction of radiation, we have X-ray and electron diffraction methods. Okay. If rotational of radiation, we have polarimetry, optical rotary dispersion, circular dichroism, and so on. If mass to charge ratio, okay, we have mass spectrometry (MS), and if the electrical potential, we have potentiometry. Other example, polarography, DTA, DAC, etc. So the most common one, okay, in our topic is emission of radiation. Oh, the circle is not so nice. Okay, emission and also absorption of radiation. This is the main one that we're gonna learn in this topic, right? Okay, so what is a spectrum in analytical chemistry? Spectrum is the data that is obtained from a spectrometer or spectroscopy analysis. Okay, a spectrum is a plot of the intensity of energy detected versus the wavelength or mass or momentum of frequency, etc. of the energy. Okay, so we have the wavelength. As I told you, the wavelength represent what is the analyte type, okay, and the absorbance, okay, how much it absorbs. Okay, this is in case of absorption of energy wavelength. So the more it absorbs, the more concentration of the analyte. Okay, this is at the left side is ultraviolet spectrometry, and the right side is infrared spectrometry. Okay, and then we have atomic spectroscopy, a measurement of the wavelength or intensity of light that is emitted or absorbed by a free atoms. Okay, for example, atomic fluorescence spectroscopy (AFS), atomic absorption spectroscopy (AAS), and atomic emission spectroscopy (AES). Alright, the molecular spectroscopy, examination of the interaction of light with the molecules. Okay, the molecules can absorb light, emit light, and scatter light. All of these interactions allow us to know the identity of a structure of the substance. For example, ultraviolet, okay, UV visible spectroscopy, UV visible, infrared spectroscopy (IR), and as well as the nuclear magnetic resonance spectroscopy (NMR). These methods, okay, is for molecular spectroscopy. We can know the structure of the molecule, okay, based on this instrumental method. All right, ultraviolet, infrared, and nuclear magnetic resonance. This is a common instrument that needed to, in order to investigate the type of the molecule. What is the possible type of the molecule? What is possible structure of the molecule? All right. And then we have absorption. This is for characteristic of wavelength absorbed and emitted. Depends on the identity of the compound, depends on the amount of the analyte present in the light path, and then remains the same regardless of the quantity of the analyte present. Okay, and then we have also interference, okay, spectral absorption of emission of the other components of the matrix. Remember, in the first chapter, for the sample preparation, we try our best to remove the matrix, okay, the contaminants from the sample, to avoid it disturbing our analyte determination. So it may be an interference during the analysis whereby the spectral being absorbed by the matrix, right? And then interference in terms of chemical materials determined are not in the same chemical or suitable form. And then instrumental interference, excess illumination due to imperfection in the instruments. All right. The complement of absorbed light is transmitted or scattered. Okay, we only see visually colors that are transmitted within the visible region. This is our normal eye can see. And in spectrochemical methods, the absorbed radiation is electronically measured. Okay. For example, this is wavelength and absorb color and transmit color. Okay. Right, as light passes through an analyte in solution, the intensity of the light is reduced. This is the basic thing of the absorption. Okay, the longer the path length, the more light is absorbed. Okay, and the higher the analyte concentration in solution, the more the light is absorbed. This is a basic thing that you need to know about the concept of absorption of the light. Okay, as light passes through an analyte in the solution, okay, the intensity of the light is reduced. Okay, so if we have for example, if we have let I use the my phone. Okay, this is, okay, our analyte in a container. If the light pass from this way, all right, and we have our detector here, okay, the detector will detect that the intensity of the light being reduced, okay, because it passed through the analyte. And the longer the path length of the for example sample container, the more the light being absorbed. If this is a sample container, okay, this is a light source, so the light is being absorbed by this sample container and our analyte inside it. If we have a bigger one, okay, the longer one, so the more light being absorbed. All right, so the higher the analyte, the analyte concentration in solution, the more light is absorbed. All right, and absorbance is proportional to the path length and concentration. This is the basic thing, right? So it is a Beer's law. We call it as a Beer's law. Statement of a Beer's law is absorbance present by A change exponentially, okay, exponentially by a function of a linear change in transmittance T. Okay, absorbance is linear to concentration, meaning that the more the concentration, the more it will absorb the light. Okay, so the less intensity will be detected by the detector. So transmittance is exponentially depends on concentration. All right, and of course it also exponent with the path length or the sample container length. So we make it constant. Okay, so transmittance T is equal P divided by P naught. Okay, absorbance A is equal to negative log T, and A is log 10 P naught times P naught over P. So A is epsilon B times C. All right, epsilon is a molar absorptivity, molar extinction or coefficient, or epsilon. Okay, and B is a path length. Okay, the path length, the B, the size of the sample container, and C is the concentration. So it is exponentially. All right, the absorbance is exponentially with dependent on the concentration and as well as the path length. So that the equation of Beer's law is A equal to epsilon B times C. Right? So A is absorbance. Okay. Epsilon is molar absorptivity. B molar absorptivity is the ability of the molecule to absorb the energy. B is the path length of the sample in cm, and C is the concentration. Okay, of course, the more the concentration, the more the absorption. Alright, so if the concentration increase, the absorbance also increase. If the path length increase, the absorbance also will increase. If the molar absorption increase, the absorption is also increase. So the Beer-Lambert law, this is an example. Okay, find epsilon, make a solution of known concentration, put in a cell of known length, measure absorption by UV visible, and we can calculate the epsilon. Alright, so find the concentration, we know the epsilon. Okay, this is according to Beer-Lambert law, so we can find a concentration. The first one, we make a known concentration of the solution, and then we measure epsilon, and then if you want to find the concentration of an unknown, so we can use the epsilon, because we already know the epsilon. Put a sample in a cell of known length, okay, it's constant, and measure the absorption by UV visible, and we can calculate the concentration. Just play with the Beer's law. Okay, for example, a sample in a 1 cm cell is determined to transmit 80% light at a certain wavelength. If if the absorptivity of the substance at this wavelength is 2.0, what is the concentration of the substance? Okay, we have A equal to log T transmission, okay, and then negative log AT per 100 is equal to 0.097. Remember, 1 cm is the path length, okay, 80% is the T transmittance, okay, and then we have absorbance is equal to 0.097. so A is equal to epsilon times B times C, so we can calculate the concentration. Alright, next example, a 1 gram tablet containing drug D with the molecular weight of 270 gram per mole has a molar absorptivity of 703 at 262 nanometer. A tablet was dissolved in 1.5 liter of water. If the solution exhibit an absorbance of 0.687 in the UV region of 262 nanometer in a 1 centimeter cell, what is the percentage weight of the drug in the tablet? Right, A is equal to epsilon BC, so we have the absorbance 0.687, and then we have the epsilon, the absorptivity. Alright, and then we have also the path length, the B, and also we don't know the concentration. So at the end we can calculate the weak percentage. Alright, remember the weak percentage. Okay, first we calculate the calculation. The calculation is to calculate the concentration. Alright, because the tablet is 1 gram, so the weight of D. Okay, so drug D, we calculate the weight first. We have the concentration, okay, 9.77 times 10 to the power of -4 mole per liter. So we can calculate the weight of the drug D. How to calculate the weight? Okay, we times the volume of the solution, because it's been dissolved in 1.5 liter of water. So we have how many gram? We times the molecular weight, so we have 0.396 gram. So the weight percentage is 39.6%. Alright, we have another example. Chloroaniline is determined by as amine picrate Alright, 0.0265 gram sample is reacted with picric acid and diluted to 1 liter. The solution exhibits an absorbance of 0.368 in the 2 cm cell. What is the percentage of chloroaniline in the sample? Given the epsilon is 1.25 times 10 to the power of -4. Alright, the epsilon, the absorptivity, and the molecular weight is given 127.6 gram per mole. Right, so the solution is epsilon A equal to epsilon BC. Okay, and then we can know the concentration. All right, and now we calculate the percentage. All right, what is the percentage of chloroaniline in the sample? Okay, we have the weight of the sample here. Okay, so we have how many gram of chloroaniline, and then we just divide by the weight of the sample times 100, so we get 7.09% of the chloroaniline. Alright, now we learn about the UV visible instrument. Okay, remember UV visible, okay, is a range of wavelength, okay, varies from 400 nanometers to 700 nanometer. All right, so this is the UV region. The vacuum UV is, the lambda is lower than 200 nanometer. So for the UV is 200, larger than 200 and lower than 450, and for the visible is larger than 450 and lower than 750. So in combination for the UV visible, this is the region. Okay, we can see only a small portion of the electromagnetic spectrum. Okay, our eyes only can see the visible light, but a lot of frequency of the electromagnetic spectrum that we cannot see by our naked eyes. All right, so the UV visible region, when the white light passes through or is reflected by a colored substance, a characteristic portion of the mixed wavelength is absorbed, and the remaining light will then assume the complementary color to the wavelength absorbed. Alright, and this relationship is demonstrated by the color wheel shown on the right. Okay, this is a color wheel. Right, this is color wheel. Here, complementary colors are diametrically opposite each other. Okay, thus absorption of 240 to 420 and 430 nanometer light renders a substance yellow. Okay, and absorption of 500 to 520 nanometer lights make it red. Okay, green is unique in that it can be created by absorption close to 400 nanometer as well as absorption near 800 nanometer. All right, we can only see a small portion of the electromagnetic spectrum in the visible region. In spectrochemical methods, the absorption of UV to far IR radiation is measured. So the UV visible instrument spectroscopy is used to obtain information about the atomic and molecular energy level, the molecular geometries, the chemical bonds, and as well as the interaction of molecules and related process. To identify the components of a sample as a qualitative analysis, and to measure the amount of the material in sample as a quantitative analysis. Right, but what makes a substance absorb UV visible radiation? Okay, how the substance absorb the UV visible radiation, so that the detector will detect the amount of absorption. Okay, so what is it? Okay, it is because the substance are chromophore. The substance that can absorb the UV visible light we call as a chromophore. What is chromophore? Chromophore is substituent atom or group of atoms. What is a group of atoms? Of course, a molecule. Okay, in a molecule that absorb light. So if the molecule or atoms then can absorb light, it is a chromophore. Okay, the color arise when a molecule absorbs certain wavelength of visible light and transmit or reflect others. All right, and UV and visible light that hits the chromophore can thus be absorbed by exciting an electron from its ground state into an excited state. All right. What is chromogen? A molecule that containing a chromophore. Okay, what is chromophore? A substituent, atoms or group of atoms in a molecule that can absorb light. So this is chromophore. And chromogen is the molecule that containing chromophore. Right? Electronic absorption bands for representative chromophore. Right? This is the example. Right? The chromophore, the system. Okay. And what is the lambda max? All right, and energy max. All right. Electrons are responsible for most UV visible electronic transition. Okay. We have type of pi electron and n electron. Okay. Pi electron is double or triple bonds, and n electron is unshared electron in the outer shell, the lone pair. All right. Right. This is the example of the pi electron and n electron. Excuse me. So the pi electron is the double or triple bond. So we have here in the NO2 molecule we have a double bond. So this is the pi electron. Okay. Remember in every bond of the atoms to another atoms there is an electron here. Okay, so this is the type of bonding have pi electron. Okay, and where is the n electron? The lone pair. Okay, the unshared electron in the outer shell. So this is the n electron. All right. So this is the electrons that are responsible for most UV visible electronic transitions. Okay, type of UV transition. Okay, from bonding excited into the anti-bonding. Okay, from the sigma bonding to pi star bonding. Okay, this is the example of UV transition. Okay, when absorb energy, it become non-bonding electron to anti-bonding and so on. Many types. Okay, we have non-bonding to anti-bonding. We have bonding to anti-bonding. We have non-bonding to sigma star anti-bonding. Okay, we represent with the symbol, the sigma, pi, and sigma star and pi star and sigma star. So chromophore is unsaturated organic functional group that can absorb in the UV visible range. The presence of the chromophore in a molecule is best documented by UV visible spectroscopy, but the failure of most instruments to provide absorption data for wavelengths below 200 nanometer make the detection of isolated chromophore problematic. Conjugation generally moves the absorption maxima to longer wavelength, and molar absorptivity may be very large for strongly absorbing chromophore, larger than 10,000, and very small if the absorption is weak, 10 to 100. This is the relationship between molar absorptivity. Okay, for strong, for very large, for maybe very large for strongly absorbing chromophore, and very small for the weak chromophore. That is the relationship between molar absorptivity and the chromophore. Okay, the magnitude of the epsilon reflect both the size of the chromophore and the probability that light of a given wavelength will be absorbed when it strikes the chromophore. Okay, a list of some simple chromophore and their light absorption characteristic is provided in the table below. Okay, we have a chromophore in terms of double bond, for example ethene. So the excitation is from pi to pi star. Okay, the lambda max is 171, the epsilon is 15,000. So the solvent should be hexane, and so on. So absorption types, it may be by organic compounds, saturated organic compounds containing heteroatoms, O, N, S, or halogens, contains non-bonding electrons, can be excited by radiation in the 170 to 250 nanometer range, or by inorganic species, ions and complex of element in first two transition series, absorb broad bands of visible radiation in at least one of their oxidation states and are colored. Okay, the inorganic species basically with colored solution, right? Absorption is between filled and empty d orbitals. The change transfer absorption by charge transfer complex CTC. All right, absorption has large epsilon, larger than 10,000. Okay, CTC. Okay, a charge transfer complex consists of electron donor group bonded to an electron transfer. Electron pair from donor is transferred to acceptor orbital. For example, iron 3 complex with 10 phenanthroline, iron 3 with thiocyanate, red color, and so on. In metal ion complex, okay, the metal ions serve as the electron acceptor. Right, UV absorbing compounds, some natural organic pigments, okay, the carmesic acid, right, from the insect Orchis cacti, and then the indigo, all right, from the mollusks of the genus Murex, all right, and then the quercetin from saffron, and B-carotene from carrots, okay, beta carotenes from carrots. A common feature of all these colored compounds displayed, okay, is a system of extensively conjugated pi electron. We have conjugated pi electron. How we know the conjugated pi electron? We have a conjugated double bond. All right. Then what makes a chromogen absorb UV visible radiation? Because chromogen has a conjugated system where multiple double or triple bonds are separated by just one single bond each. A conjugated system requires that there is a continuous array of pi orbitals that can align to produce a bonding overlap along the whole system. Okay, if a position in the chain does not provide a pi orbital, or if geometry prevents the correct alignment, then the conjugation is broken at that point. Right, conjugation of double and triple bonds are shift the absorption maximum to longer wavelength, like the spectrum at the left. All right. Okay, this is the conjugate triple to double bond. Okay, conjugate of double and triple bond are shift the absorption maximum to longer wavelength. All right. Okay, this is 230 nanometer. Right, from the Pauling spectra left, okay, it is clear that each additional double bond in the conjugated pi electron system shift the absorption maximum about 30 nanometer in the same direction. Okay, you see this, okay, from the first one, okay, the conjugation of double and triple shift the absorption maximum to longer wavelength. Okay, right, and then the bottom one, okay, from the Pauling spectra, each additional double bond of the conjugated pi electron shift the absorption maximum of 30 nanometer. Right, you can see the shift here, okay, with the same direction, it's shift about the absorption maximum about 30 nanometer. Right, the molar absorptivity, okay, the epsilon roughly doubles with the with each new conjugated double bond. Appearance of several absorption peaks or shoulders, usually solvent dependent. Okay, we have, for example, we have the look at the bottom picture. We have green, purple, and blue. Right, we can see the shift, okay, due to the conjugated pi electron system, shift the absorption maximum 30 nanometer in the same direction. Okay, you see, and also increase, okay, the epsilon with every new conjugated double bond. All right, a comparison of the absorption spectrum of one pentene with lambda max of 178 nanometer with the isoprene, okay, the left side, clearly demonstrate the importance of chromophore conjugation. Okay. Right. What is auxochrome? Auxochromes are substituent groups which are not themselves optically active. Okay. What is the optically active? Remember, chromophore. Then the molecule that containing a chromophore we call as chromogen. And what is auxochrome? Auxochrome are substituent groups which are not themselves optically active in this energy range, but interact with other chromophore to shift both intensity and wavelength. For example, hydroxyl, amines, and halogens. They provide unshared protons, unshared electrons, and that interact with pi electrons in the chromophore, and to pi conjugation. Right? Okay. What is auxochrome? Group of atoms attached to a chromophore. Remember, auxochrome initially is not optically active, right? It attached to a chromophore which modify the ability of the chromophore to absorb modify the ability of that chromophore to absorb light. A functional group that does not absorb in UV region but has the effect of shifting chromophore peaks to longer wavelength as well as increasing their intensity. Right? Right, this is example of auxochrome function group. Okay, phenol, phenolate ion, aniline. Okay. Okay, what is UV visible instruments? Okay, the single beam spectrophotometer, and also we have a multi-channel spectrometer and double beam spectrometer. Okay, type of UV visible instrument. The first one is single beam spectrometer, employs a single source to supply radiation to the sample, then the background in turn. Advantage is the single set of components required complex device may be incorporated, and the disadvantage is separate correction must be done for background spectrum due to solvent or matrix interference. Need a longer time. Okay, this is a simple of this example of the single beam spectrometer of UV instrument. This is the source, okay, the single source, okay, single beam source. Okay, we have a filter, and then we have a shutter, and then reference cell. Okay, and then we have a sample cell here. Okay, a photo detector and amplifier. Okay, and then we have double beam. Okay, double beam. This is also we have source of the wavelength of the light. Okay, and we have a filter here, and then there will be a two beam separated into two beam. Okay, we have two shutter, okay, and mirror. Okay, the beam will be split, all right, to reference cell and sample cell, and then the photo detector. Okay, and then different amplifier. And then lastly we read the measurement of the absorption. Right, it's instrument architectures. Okay, the instrumentation, we have a source, a D2 lamp. Okay, or we can also have a xenon lamp or tungsten filament halogen lamp. We have a wavelength selector. This is a source. All right, the entrance slit, wavelength selector. Okay, in this case, this is the wavelength selector, the monochrome. Right, then we have the sample cell, and then we have the detector. In the detector, sometimes phototube, photomultiplier, a photodiode array, CCD, and so on. And then we have a signal processor. Our computer will read the signal and transform into a and translate into a readout into the information that we can read. Right, instrumentation, components of optical instrument. We have source. This is basic diagram you need to know about UV. Source of the wavelength of the light. Okay, we have monochrome, we have sample, detector, and recorder. Okay, so this is a sample of light source. Right, we have deuterium and hydrogen lamp. We have that covers the UV range 200 to 330 nanometer. We have the tungsten 330 to 700. We have tungsten halogen 330 to 3000. Okay, this is the range of the wavelength covers for every type of the light source. Okay, so the wavelength selector, we have photometer and spectrophotometer. So for the photometer, use filter to select. In the UV, we have a type of photometer that have or use filter to select the wavelength and can only detect single wavelength at time. Okay, two type of filter: interference filter and absorption filter. And we have also monochromator. Okay, a grating or a prism. Okay, allow them to scan various wavelength, and input may be a continuum source of or line source. All right, and also we have filter, interference filter, and absorption filter. For interference filter, it will remove selected wavelength by internal destructive interference and reflection, and transmit a narrow range of wavelength based on constructive or destructive interference for light bouncing between two reflectors separated by a dielectric layer. Okay, where D is the thickness of the dielectric, N is the index of the refraction of the dielectric layer, and M is the order of the wavelength. Just the filter is just about to remove the interference or adsorption filter used to absorb unwanted wavelength. Okay, the filter mostly function is to remove out the interference and the absorptions that we don't want in the analysis. All right, so the filter, the advantage of filter is low cost, simplicity, ruggedness, okay, portability, and easy to maintain. Disadvantage is a lesser versatility, inability to generate entire spectra, and generally wider effective bandwidth. Okay, so we have monochromator. Okay, entrance slit provide a light source of well-defined dimension, usually rectangular with width W and height. We have a collimating lens. Okay, we have a dispersing device, usually a prism or grating, and we have a focusing lens and exit slit. This is the example of the monochromator prism. So the operation of monochromator, okay, polychromatic radiation or radiation of more than one wavelength enters the monochromator through the entrance slit. The beam is collimated and then strike the dispersing element at an angle, and then the beam is split into components wavelength by the grating or prism. Okay, and by moving the dispersing element on the exit slit, radiation of only a particular wavelength leaves the monochromator through the exit slit. So the function of the monochromator is to select the wavelength that we want, because from the source of the radiation okay, from the beam we have a various, okay, a polychromatic radiation. So we need only a monochrome, okay, a certain wavelength that we want for the UV instrument. So it's like a filter also, but it is called as monochrome. The type of filter is monochrome. So both monochromator or filter is to isolate the desired lambda band, so that only the band of interest is detected and measured. So we don't want the entire wavelength of the from the source of the light, which is from the beam. Okay. So the filter and monochromator comparison. Okay, for the filter provide low resolution lambda selection, and for monochromator produce high resolution. And for the filter is suitable for quantitative work, and monochromator both qualitative and quantitative. For the filter, lambda cannot vary continuously, and for the monochrome, lambda can vary continuously. So monochromator are the better one. These are wavelength selectors, dispersive element and filters. Okay, so we have multi-channel spectrometer. Okay, the source of supply with a wide range of frequency radiation. Okay, polychromatic source. Okay, and we have lens, sample cell, and then a grating and photodiode array detector. Okay, this is sample cell. Remember in the Beer law. Okay, so the length of the sample cell is represented by B. It's already calculated in the instruments. Okay, the cell cuvettes, we call as cuvettes, are selected appropriately based on wavelength requirement. Okay, we have the sample cell made from quartz. Okay, the fused silica is for the UV visible, and we have a silicate glass for visible and plastic for visible. Normally we use quartz. All right. So remember in the Beer's law, we have A equal to the absorbent equal to epsilon times B times C. So the sample cuvette is represented by B, the path length is represented by B, right? So we have diluted sample, we have a special cuvette for dilute sample, and as well as the concentrated sample. Okay, the flow cell, the spec ecam, okay, everything and so on. All right, this is the type of a sample cell and the wavelength that we work with. Okay, we have a fused silica quartz, okay, for the vacuum UV to near IR, okay, and almost IR. Okay, so depend on the type of the sample cell material. So the precaution when using UV visible is to keep the cuvette clean, because your fingerprint also could could differ, or could it will affect the result. Okay, it will affect the spectrum that you need. Okay, don't clean with paper products, use optical paper. Store dry and store carefully and gently, and don't get fingerprint on them. Use the same sample cell during running the blank, standard and sample. Okay, the sample should be solvent. Okay, concentration typically lower than 50 micromolar. Solubility, ionic strength, hydrogen bonding, aggregation, pi stacking, solvent absorption. Okay, and so on. Okay, common solvent cutoff in nanometer is with this range. Water is not 190, acetylene 190, and so on. Okay, phase spectra can be useful qualitative tools. The spectrum in the gas has many lines due to electronic vibrational and rotational transition, while in non-polar only electronic transition can be observed, and in a polar only give a simple smooth absorption band because the intermolecular forces. And now we have a detector, okay, that detect the absorption of the wavelength of the light. It will detect how much it lost and then translate into an electrical signal. Okay, this high sensitivity, okay, high signal over noise ratio, Okay, and then constant response for lambdas and fast response time. This is the criteria for the detectors. Okay, we have a single lambda detection diode and PMT. Okay, full spectra detection, we have CCD and diode array. This is type of detectors. Okay, this is the table uh, about the lambda, the wavelength, and type of the detector. We have photon detectors and thermal detectors. The photo multiplier, what is the function of the photo multiplier? Detect one wavelength at a time, and based on the photoelectric effect, photocathode and series of dinodes in an evacuated glass enclosed. Okay, and then photon strike cathode and electron are emitted. Electrons are accelerated towards a series of dinodes by increasing voltage. Additional electrons are generated at each dynode. Amplified, the signal is finally collected and measured at anode. This is for, to multiply the response. Okay, to ease the detection process. This is a function of the photo multiplier. So how does the PMT function? A photon or radiation entering the tube strikes the cathode and causing the emission of several electrons. Okay, and then these electrons are accelerated towards the first dynode. Okay, more positive than the cathode, and then the electrons strike the first dynode, causing the emission of several electrons for each incident electron. So it will multiply the response. Okay, these electrons are then accelerated towards the second dynode to produce more electrons, which are accelerated towards dynode 3 and so on. So it will be multiply itself to ease the detection. So the algorithm in the instrument will calculate then how much is the actual actual absorption by the solution, and for the multiplying process is just to ease the signal to be detected. All right, see, this is how it will be multiplied. Okay, the photo multiplier tube. Photodiode arrays measure several wavelengths at once. All right. Detection in some simultaneous ICP OES. Right, this we will learn after this in ICP OES instrument chapter. Okay, for the instrumentation, we have full spectra detection and single wavelength detection. Okay, and we have for full spectra we have source, sample, and then the monochromator, and then the detector. And for the single lambda detection, we have source, then we have sample, and we have the detector. Okay, that is the different: source, sample, monochromator, and array detector. For single lambda, we have source, monochromator, sample, and point detector. And for the full spectra, we have array detector. All right. Okay. This is the example of the spectrum. Each transition results in a single peak, as shown by the spectrum, except for the rotational and vibrational transitions that cause broadening of the peak. Okay, the spectrum is a plot of intensity of energy in term of light detected versus the wavelength, mass, momentum, frequency, etc. of energy. It is data obtained from a spectroscopic analysis. Okay, this is example of the UV peak for iron 3, iron 2, and iron 3 oxide. Okay, this is example of the spectra. Alright, for the quantitative analysis, okay, in any quantitative analysis involving an instrument, we need to do the calibration plot, okay, or calibration curve. The linear calibration curve must be constructed to determine the concentration of the analyte. Remember, the instrument, all the instrument, they are not able to describe the concentration of any solution, except we set the calibration curve so that the instrument know this response is from this certain concentration. Right? There are two types of calibration, the preparation of the standard calibration. The first one is standard addition method. It's able to compensate for matrix effects, use the complex samples, and the second one is internal standard method, able to compensate for random and systematic errors, but it is a difficult method. Okay, for UV spectroscopy, practicalities is referencing. Okay, matrix, which is solvent, buffer, etc., might also have absorbance, so we must be taken care of in dual beam. Okay, simultaneous measurement of reference cell eliminates absorbance of background, and recording of baseline recommended. And then we have single beam, requires measurement of reference spectrum, can be subtracted from the sample spectrum, and preferentially in same cuvette. Right, this purpose is to remove the absorbance from the matrix. We only want the absorbance from the analyte. Alright, this is the method to correct the background. Okay, so A is equal to negative log T transmittance, or equal to log P null over P. Alright, we want to know A, which is log P null over P. So for our sample, not the matrix. Analyte in the sample, not the matrix. So this is to correct the absorption, correcting the background, remove the background. Right, so the absorption from the cuvette plus the solvent and plus the sample is total absorption. Alright, so absorption of all plus the absorption of cuvette, okay, the sample vials, absorption of solvent, and also absorption of the sample, which is a total absorption. So we need to deduct, okay, to remove the absorption from the cuvette as well as the solvent. So background is only from absorption of cuvette and absorption of solvent. So we need to deduct both of the absorption. So absorption of all, if we deduct the background, we will have the absorption of the sample. Okay, for the single beam instrument, sequence of the events is light source. Right, I need a pen now. Okay, this is a light source, and then reference in holder number 2, open shutter, and then measure light P0. Okay, and then raster lambda and repeat for close shutter, sample cell in holder. Where is sample cell? Okay, this is sample cell. Okay, and open shutter. Okay, and measure intensity here, and raster lambda and repeat 9, repeat with method 9, measure intensity, and then close shutter. There are pros and cons of single beam instrument. The pros is simple, less expensive, less optic, less moving parts, higher light intensity, and can use the same cuvette. And the cons is change over time, better for short-term experiments and manually move sample. For double beam instrument, spatially separated and also temporarily separated. Right, the compensate for lamp fluctuation, temperature change, amplifier change, electromagnetic noise, and voltage spikes, and also continuous recording. Right. For the double beam instrument spatial, okay, the sequence is when the light source is on, the reference and sample in holder. Right, we have reference cell and sample cell, and then open shutter. Where is the shutter? Here. Okay. Okay, and then measure detector 1 P null and 2 P here and here, and raster lambda and repeat 4. Okay, repeat 4 again, repeat measure detector, and then close shutter. Okay, then we have the absorbent. So the pros of the double beam, both samples simultaneously, less moving parts than temporal, the cons are two different cuvettes. We need to have two different cuvettes and two different detectors, and then half the intensity and more expensive, right? For the double beam instrument temporal, okay, the sequence of the events are, the first one is light source on, okay, and then reference and sample. We have reference and sample, and then rotate the chopper. We have a chopper here now. Where is the chopper? Right, and then open the shutter. I can't see where is the chopper. Okay, all right, open the shutter. Where is the shutter? Okay, and then monitor detector, right, and then raster lambda and repeat number 4, open the shutter, and then close shutter. Then we have the absorbance. So pro and cons, both samples simultaneously and same detector. The cons are two different cuvettes, half the intensity, rotating mirrors, and not really simultaneous. Okay. Sometimes there will be a deviation from the Beer's law, and the causes of deviation from Beer's law are, the first one is the instrument limitation in terms of resolution, signal noise to ratio, okay, and then stray light and contamination, and also sample limitations, the molecular interaction within the sample, inside the sample, the associations, the H bonding, the hydrogen bonding, and as well as the reactions in the sample and refractive index change. Right, next. Right, you can read all this. Okay, and now we have several application as example of the UV analysis. UV visible analysis, for example, analysis of vitamins, fatty acids, analgesic tablets, proteins, trace metal, as well as food coloring. Okay, let's see. All right, this is a concept. Okay, quantitative analysis by molecular absorption, or we call as colorimetry. Okay, this is application of the UV. Okay, and because the absorption of spectroscopy is widely applicable, sensitive, selective, and accurate, and easy, 95% of the quantitative analysis in field of health performed with UVN, visible test. Hemoglobin in blood, also we use UV visible. And the first step in analysis, establish working condition. We have to select lambda, the selection and cleaning and handling of cells, calibration. Okay, we need to calibrate of course for the quantitative in determining the relationship between absorbance and concentration. Right, this is the example of the colorimetry instrument, Hatch instrument. We can measure nutrients. Okay, we can select the method here. If we want to measure nutrients, okay, we need the nutrients reagent. We digest the sample inside the nutrient reagent first, and then we can measure specifically type of nutrient, for example, nitrates, nitrogen, phosphorus, and so on. We have this instrument in our lab. Right, this is the SOP for analysis of ammonia nitrogen parameter. We have the specific reagents, okay, to be digested with the sample, okay, and then we must set the instrument for ammonia nitrogen. Then after digesting the sample, we put the vial inside the instrument, and then we just scan, and we know quantitatively how much is the ammonia nitrogen inside the sample. Right, there we have the amount, right? Okay, this is the cuvette or sample vial compartment. Okay, select the methods here, and then we can scan, read the sample, and then we have the concentration. And then the application, another application is analysis of hexavalent chromium, okay, using spectrometric method. Okay, this is the example of students' work, right? Hexavalent chromium is specifically for COD determination or chemical oxygen demand. Okay, you can read this. Okay, this is the example of student slide using the real instruments. Okay, with the application of UV visible. And then we have analysis of synthetic colors in food samples using UV visible spectroscopy. All right, you can read the works. Okay, this is the last slide. All right, for the example of UV visible, I think this is all for today. For now, for this chapter of the first instrument, which is a UV visible spectrophotometer, in the chapter of spectroscopy analysis. Okay, we will move to next chapter, which is about the atomic absorption spectrophotometer and AES, atomic emission spectrophotometer, AAS and AES. Okay, all right. In applying the method of spectroscopy analysis. Okay, I think we need to move faster after this, either synchronized or unsynchronized, because before mid-sem break, we have to finish until the chromatography technique. We have several instruments in chromatography technique, several methods. So inshallah we can do it. All right. See you again. Assalamualaikum.